All right, let's jump right in today. We're going deep on something called the ether of space.
I know it sounds a little bit like something out of science fiction, right?
A little bit. But back in the early 1900s, this wasn't fiction, it was serious science. Scientists were convinced that this mysterious substance was everywhere.
Like literally filling up the entire universe.
Yeah, they thought it was like the very fabric of reality, the stuff that held everything together.
We're talking about some pretty brilliant minds here, too. So what led them to believe in this invisible ether?
Well, it all started with light. They knew that light behaved like a wave.
Yeah, and waves need something to travel through, right?
Exactly. Think of ocean waves. They need water. Sound waves need air.
So they figured light waves must need something, too, even in the vacuum of space.
Right. They couldn't wrap their heads around light traveling through pure nothingness. So they came up with this idea of the ether, this invisible stuff that permeated all of space. It was like the cosmic ocean that light waves surfed on. Okay, so we've got this invisible ether, this cosmic ocean. But what was it like?
Hmm, that's where things get a little tricky. Scientists realized that this ether had to have some pretty contradictory properties.
Contradictory. Like, how so?
Well, on the one hand, they knew that light travels incredibly fast, right? So for the ether to carry those light waves at such high speeds, it would have to be incredibly rigid, like even more rigid than steel.
Okay, that makes sense. But you said contradictory. What's the other side of that?
At the same time, planets and stars are moving through space all the time, without any noticeable resistance.
Whoa, wait a minute. So it's supposed to be super rigid, but also offers zero resistance. How is that even possible?
Exactly. That was the big dilemma. It seemed impossible for something to be both incredibly dense and also completely frictionless.
You'd think that would be a major red flag. Did any scientists raise concerns about these, like, almost impossible qualities?
Oh, absolutely. There were tons of debates and arguments about the nature of the ether, but there was also this intense drive to prove its existence experimentally.
So someone had to try and, like, catch this cosmic phantom, right?
Yeah, and one of the scientists who really went all in on this was Sir Oliver Lodge. He was a brilliant British physicist who was just obsessed with the ether.
Okay, Sir Oliver Lodge. What did he do?
Well, he designed all these elaborate experiments to try to detect the ether. He even built this massive contraption called an ether machine.
An ether machine. What did that even look like?
Well, it involved these huge, heavy steel discs that he spun at incredibly high speeds.
What was he trying to do with that?
His idea was that if the ether existed and was being dragged along by these spinning disks, it should have a measurable effect on the speed of light passing through them.
Oh, I see. So if light travels differently near these spinning disks, then that's evidence for the ether. Pretty clever. Did it work?
Well, despite all of Lodge's efforts, his experiments didn't detect any change in the speed of light whatsoever.
So, back to square one.
You'd think so, right? But Lodge was not easily deterred. Even though he couldn't prove it experimentally, he still believed in the ether. And, get this, he even tried to calculate its density.
Its density. But if it's invisible and undetectable, how could he even begin to calculate that?
Well, he based his calculations on the presumed properties of the ether, the rigidity and the speed of light and all that. And his results were, well, pretty mind-boggling.
Okay, I'm on the edge of my seat here. What kind of density are we talking about?
He estimated that a single cubic millimeter of ether.
Hold on. A cubic millimeter, that's like tiny, smaller than a grain of sand?
Yeah, exactly. He believed that a cubic millimeter of ether would weigh 1,000 tons.
1,000 tons? Are you serious?
That's what his calculations suggested.
So he's proposing that this invisible stuff, which apparently offers no resistance to planets and stars, is also thousands of times denser than anything we know.
Yeah, that's where things stood with Lodge. He tried to explain this apparent paradox by suggesting that matter, as we know it, is actually made up of tiny, incredibly dense knots in this smooth, uniformly dense ether. He called these knots electrons.
So hold on, if I've got this right, he's saying that everything we see and touch, everything in the entire universe is just like little whirlpools in this vast, invisible, super dense ocean of ether.
Pretty much. That was Lodge's vision of reality.
It's an incredible picture, I have to admit, but it still leaves a lot of questions unanswered. Like, where does gravity fit into all of this? How does this super dense ether explain the force that literally holds the universe together?
Well, Lodge had some thoughts on that too. So Lodge had some pretty interesting ideas about gravity too. Remember how he thought the ether was super dense?
Yeah, 1,000 tons per cubic millimeter. Hard to forget that.
Well, he believed that despite despite its density, the ether was also under immense tension, like a tightly stretched rubber sheet. And he thought that matter, those little knots or electrons he talked about, would create disturbances in this tension.
Disturbances? Like how?
Well, imagine you poke a finger into that stretched rubber sheet. It creates a dip, right? Lodge thought matter did something similar to the ether. Each bit of matter created a kind of gradient in the ether's tension.
Okay, I think I'm following. So instead of objects pulling on each other directly, they're actually creating these little dips in the ether.
Exactly. And those dips are what cause objects to move towards each other. That's what we experience as gravity.
So it's not a force in the traditional sense. It's more like objects falling into the dips created by other objects in this ether sheet. Mind-blowing. But, for all of Lodge's ideas about the ether, there was this one experiment that really threw a wrench into the whole thing.
You're talking about the Michelson-Morley experiment.
The one and only. It's kind of a legendary experiment in physics, isn't it?
It really is. Especially because it was designed to detect the ether, but totally failed to do so.
Yeah, it's like they set out to catch this mythical creature and came back empty-handed. So how did this Michelson-Morley experiment actually work? What were they trying to do?
Well, their goal was to measure how the Earth's movement through the ether affected the speed of light. They figured if the Earth is orbiting the sun, it must also be moving through this stationary ether.
Right, like running your hand through water. You can feel the water moving past you.
Exactly. They called this the ether wind. And they believed this ether wind should affect the speed of light depending on whether the light was traveling with it or against it.
Okay, so they were looking for these tiny differences in the speed of light caused by the ether wind. How did they measure that?
They built this ingenious device called an interferometer. It was designed to split a beam of light into two parts and send them on different paths at right angles to each other.
And then what?
Well, the idea was that one of those beams would be traveling with the ether wind and the other against it. And this should cause a tiny difference in their speeds. When the beams recombined, this difference in speed would create a noticeable shift in the interference pattern. It's a bit like two swimmers racing in a river. The one going with the current will be a bit faster.
So if they saw this shift in the interference pattern, that would be evidence for the ether.
Precisely. They even repeated the experiment at different times of the year, because the Earth's motion around the sun should change the direction of the ether wind.
So they were being thorough. Did they find anything?
That's the thing. They found absolutely nothing. No matter how they oriented their interferometer, no matter what time of year they did the experiment, the speed of light was always the same.
So no ether wind.
No ether wind. And this was a huge problem. I mean, it was one of the most important failed experiments in history. It really forced physicists to confront the possibility that the ether just didn't exist.
So what happened then? If the ether was out, what was left? Did physics just grind to a halt?
Not exactly. It was more like a paradigm shift. And leading the charge was, you guessed it, Albert Einstein.
All right, so we've seen how this idea of the ether really dominated physics for a long time. But then that pesky Michelson-Morley experiment came along and threw everything into question.
It definitely shook things up. Imagine building your whole understanding of the universe on this foundation of ether, and then, boom, that foundation starts to crumble. What do you do?
Yeah, it must have been a pretty disorienting time for physicists. So where do they go from there?
Well, that's where Einstein comes in. He steps onto the scene and basically rewrites the rules of physics.
Yeah, Einstein, the ultimate physics rock star. Everyone's heard of him, but I'll be honest, his theories can be a little intimidating. Can you give us the crash course on relativity? How does it connect to all this ether business?
Sure. Before Einstein, everyone assumed that space and time were absolute, meaning they were the same for everyone, everywhere. Like, imagine a train moving. It doesn't matter if you're on the train or standing on the platform, its speed is the same.
Right, that makes sense.
But Einstein realized that the speed of light is the one thing that's absolute. It never changes no matter how fast you're moving or in what direction.
So it's like a cosmic speed limit that everyone has to obey.
Exactly. And this realization had huge consequences. If the speed of light is always constant, then something else has to be flexible. And that something else is space and time.
Wait, so you're saying space and time aren't absolute, they can change?
That's right. They're relative, meaning they depend on your frame of reference, on how fast you're moving. It sounds crazy, but it's true.
Okay, my brain's trying to catch up here. Can you give me an example?
Imagine two people. One standing still on Earth, and another zipping through space in a super fast rocket, close to the speed of light. Now, for the person in the rocket, time would actually slow down relative to the person on Earth.
Seriously, so time is literally moving at different speeds for them.
Yep. This is called time dilation, and it's
Right.
one of the crazy but true consequences of Einstein's theory of special relativity.
Okay, so Einstein comes along and he tosses out the ether and replaces it with this whole new understanding of space and time. But, it makes you wonder, did those earlier scientists, the ones who were so convinced about the ether, did they contribute anything to this revolution in physics?
Oh, absolutely. Their work was essential. Even though the ether turned out to be a dead end, the questions they asked, the experiments they designed, it all paved the way for Einstein's breakthroughs. It shows that even wrong ideas can be valuable if they push us to ask better questions.
I like that. Sometimes being wrong is just part of the process of getting closer to the truth.
Exactly. And Einstein didn't stop with special relativity. He also developed his theory of general relativity, which completely redefined gravity.
Ah, yes, general relativity. That's the one with the warped space-time and all that, right? I've always struggled to wrap my head around that one.
It's definitely mind-bending. Basically, Einstein said that gravity isn't a force in the traditional sense. Instead, it's a consequence of the curvature of space-time.
Curvature of space-time, what does that even mean?
Think of it like a bowling ball on a trampoline. It creates a dip, right? Well, massive objects like stars and planets do the same thing to space-time. They warp it, create these curves and dips.
So gravity isn't a force pulling things together. It's more like objects are just following the curves in space-time created by other objects.
You got it. It's like those dips in the trampoline guiding the path of a marble rolling around it.
Okay, so we've gone from this mysterious, invisible ether to a universe where space and time themselves can be warped and curved. It's a lot to take in.
It is, isn't it? But it's also incredibly exciting. And the best part is, we're still learning. There's still so much we don't know about the universe and how it all works.
And that's what makes it so fascinating. The quest for knowledge never ends, does it?
Never. And that's the beauty of science. There's always a new mystery to uncover, a new challenge to tackle.
Well, on that note, I think it's time to wrap up our deep dive into the ether of space.
It's been a fascinating journey through history and physics.
Thanks for joining us, and remember, keep asking questions, keep exploring, and never stop being curious about the universe and everything in it.